In previous videos, we talked about the shape of the pupil, the diameter of the pupil, the response time of the pupil. Right now, in this video, we want to talk about the obliquely viewed pupil, which means that when you look at the pupil at an angle, and what is the optical effect of having an object in an angle. So first, we need to talk about distortion aberration. Distortion aberration, we have it's a kind of aberration that we have in all optical systems, which relates to the magnification of an image at different locations on the CCD or on image plane. For our eye, we can say on retina. And we have two kinds of distortion. One, we call it barrel distortion. Let's say you start from a grid with constant distance at the object plane, and at the image plane, we have something like this, that the distance is a function of location. And we have another kind of distortion that we call it pinch Cushing distortion, that the image is like this. So this one, because it looks like a barrel, that's the reason that we call it barrel distortion. So now in our eye, and a distortion aberration at least is a function of image to the power of 2 squared of the image size. So for example, when you have 3 different oranges, small, medium, large, the aberration for the largest one is the maximum, because it's a function of d to the power of 2. So in our eye, we have a negative pupil distortion, and that negative pupil distortion causes the magnification to be a little bit smaller than the magnification that is predicted by Gaussian optics for most schematic eyes, like Gaussian model. For Gaussian model, we keep the pupil at constant diameter, but that one is not pretty correct. So when you have no distortion, the image is like this. When you have positive radial distortion, this one we call it positive distortion. This one we call it negative distortion. That the image is gonna be like this. So as you can see here, for Gaussian number 1 eye model, the paraxial one, which is this one, the magnification is not a function of a stop diameter. So the stop diameter can be from 0 to 8. You can see we have a constant magnification, which is 1.13. So we have a small amount of magnification, but based on different model, more actually accurate model, we should have something like this, that when the pupil size get bigger, because then you have distortion aberration, and that distortion aberration itself causes decrease in magnification. So you can see for a very small diameter, we have a small distortion, and then when the distortion get bigger, negative distortion get bigger, magnification goes lower, and at very big stop diameter, we have a pretty low magnification. So in a better or corrected models, we can have a magnification as a function of stop diameter. So, but the stop diameter is very complicated, because the stop diameter itself is a function of the direction actually. When you have an optical system, when you look at it from the front, the direction of the view is from the front, then you can see something like exactly like this, which is a circular aperture. But when you increase your angle, for example, when you look at it at 60 degrees, you can see something like this, because that's a projection of radial circle at 16 degrees. Then 75 get smaller, and at 90, you can see a line. So the diameter in tangential direction is a function of d. Let's say we have, at first we have diameter d, ds is equal to d, and this direction is d, this direction is d tangential. So we start, the total area, because it's a circular object, is pi ds dt over 4. But dt is a function of cosine theta or theta. So if we put dt from this equation, then we can say the area itself is a function of theta. So in order to look at this equation, again, dt is a function of cosine theta, ap is pi ds dt over 4, and ap, right now we can say ap, which is the total area, is a naught of p, which has cosine equal to 0, time cosine theta. And then, a dot of p is pi d over 2 over 4. That, from this equation, we just put d for everything because angle 0 is the same. So then we can say this is the area of the entrance pupil. So right now we have a good equation for magnification, for the area of the pupil that is related to the magnification when we are looking at different angles. But in reality, it's not like this. This research group, they did a lot of research about the entrance pupil. And during that accommodation process, and when we look at different objects in different angles, a lot of things happen. The stop moves forward, get tilted, move out of a single plane, undergo asymmetric changes, and center no longer coincide with the on-axis center. So because of all of these parameters that are changing, we need to do some kind of correction into that simple formula. And the correction into that simple formula is like this. dt over ds, instead of being 1, we have 0.99 cosine of theta plus 5.13 over 1.121. So that's another equation that instead of putting a simple equation, we actually put some kind of correction into that equation, and the correction are based on this. And based on this correction, we can see we have a this dash line is just a very simple equation, cosine theta. But that's with that correction, we can get a better result at different angles. And this side is the temporal side. This side is the nasal part. As I always mention, nasal is the direction of our nose, temporal and opposite. So when we look at our eye from different angles, the visual field angles is not completely symmetric. You can see the actual model, just cosine theta, is completely symmetric. But in reality, it's not that much symmetric. More, the result is skewed to the temporal side. So that's another model. And here are some references that I use. Thank you very much.